The first 3 weeks of the eruption here in Hawaii, crazy things would happen in the middle of the night. A new fissure would open up and it would threaten a new neighborhood. Thousands of people were evacuated from their homes. I started the Hawaii Tracker Facebook group to help people understand what's going on and get their questions answered.
Hey, how's it going? We're live. This is Fissure 20.
We had hundreds of people all throughout the neighborhoods sending in videos, articles, and images. We spend a lot of time making sure the accurate information gets out.
This is live. There's still lava moving.
They weren't just sharing a story, they were helping their neighbor. If a family was being evacuated, a group would just jump in and help out. So it was huge. They were watching out for each other.
Hello everybody, thank you for coming. Thank you for the support from everybody.
As we go through this, we're growing closer together as a community. When tragedies like this strike, you really realize how much you need each other.
Aloha everyone, I'm geologist Philip Ong, here with Mr. Dan DuPont of HawaiiTracker.com, bringing you guys another Hawaiian Volcano Tracker update. Today is Thursday, March 2nd, 2023, and there's not been a whole lot of action on Kilauea. It's been pretty rainy. There's a little bit of activity to talk about. There's still lava, so we'll go over the details of that. And seeing as there's still rainfall, we'll talk a little bit more about the rain connection to volcanoes, the recent discussion and literature that happened, and along those lines, talk about the triggers for the 2018 eruption, including potentially rain there. So that's on the menu today, Dane. Really not a whole lot of activity. Mauna Loa is still quiet. How you doing today?
Oh, doing pretty good, Yeah, definitely. It's been a real rainy week down here at Lower Leilani Estates in the area of Fissure 8, but it's been probably like that all over the island, at least on the east side. And yeah, it'd be interesting to go back over some of the literature that's been coming out recently about the connection to 2018 and the triggers of that.
Shoots. Yeah. So we'll go through it. We might be a little shorter than usual today because of the drop in activity here. There's not as much stuff to show you guys. We will show you plenty still, and as usual, I might end up going a full hour. Every time I say we're going to go short, we end up not. So we'll see how it goes here. But let Dane know if you have any questions. He'll be leading discussion on the chat and checking for any issues with our stream. Let him know if you have any issues with our audio or video. We are, as always, trying to improve and debug. and I don't think we've quite nailed it. We made some strides last week, but we'll just keep working on it. I appreciate your patience.
Yeah.
Yeah.
I mean, really, we don't have all that much. So, I mean, Two Pineapples is in chat, and I don't think they've been able to film, and we haven't gotten many things submitted. So, a lot of people, it's not the greatest viewing up there unless you like to see the steam dance, and then you're getting a full show.
Yeah, it's actually been really rainy where I live, not too far from the national park. But I've been looking at the webcams and the rain gauges from the national park, and it's actually a little bit clearer up there, a few miles away, than it is right here. And here's a live view of the lava lake right now from the USGS live stream showing on camera, and clear view down there. And we've seen times when the camera is totally obscured by the rain clouds. So this is also part of the whole issue people have with the rainfall trigger, is how variable the rainfall can be place to place on the island. Even right now, it's hard to tell what's happening up the road from you. Although it seems like recently I'm hearing reports of road flooded in Hilo, trees down by Nana Valley, up by Waimea, so it does seem to be pretty wide effect on the island, this weather pattern here. Well, turning to volcanoes, we can get into it here. Let me get the right screen up for you guys here. And we'll start with our Hawaiian volcano summary. So, all right. So here's this week's Hawaiian volcano summary. On screen, you see a live camera from the USGS showing the activity within the lava lake. It's mostly crusted over at this point in time and having occasional overturns of lava. So there is still lava flowing very weakly in this western basin, which was the site of the 2021 and 22 eruption here. If I play for you guys the thermal camera, and this is cleaned, I've taken out the bad frames so you can see a little easier, but it's not exactly continuous. It still gives you an idea of the pattern of activity in a lava lake for the last couple of weeks here. And it started off with more circulation last week, but really over the last week here, it's the most recent week, it's reduced its activity from constantly circulating to kind of pulsing, overturning. This is a process where the gas builds up beneath the crust, pops up and through, and then brings lava to the surface. The whole thing kind of convects and freezes again. It just goes through this pulsing, overturning process. That's what you guys are seeing spit up here on the screen for the last 2 weeks. So there are still times when there are no lava visible, but there are times when you do see the whole thing flash open as it overturning there. Less activity on the surface. At depth, I thought I would just show this one plot of GPS distance from north to south across Kilauea caldera. This is for the whole last year. So if I zoom in here on the last month and a few weeks, you can see that the distance from north to south across the caldera has been increasing over that similar period of time. We've seen a decrease in activity at the summit, at the surface. So it does appear that magma is still coming into the volcano. It's just not making it all the way to the surface as efficiently. However, the USGS still reports that there is tremor ongoing at the summit. It has decreased as well, so not as much as coming from that lower part of the volcano into the summit lava lake area. It appears like some might still be coming through, but enough is not getting through to show us this GPS signal that you see on the screen here. So that's the short story in Kilauea. We'll have to wait and see what happens next. In the past, we've seen these slowdowns in the eruption actually be just pauses and eruption resume. We've also seen it shut off entirely in response to external factors like Mauna Loa erupting in December of last year, November, December last year, and previously back in May of 2021 when it actually went into a 4-month break in the action. So we'll have to wait and see what happens, and that's a long and short of it this week. So let me get this cleared on the screen here, and I'll show for you guys next. Actually, this week we'll start with Mauna Loa because it is so quick. I just wanted to put on here on the screen the USGS Mauna Loa update. Let me find the right subtitle for us here. All right, Mauna Loa monitoring. So the USGS report is the same as it's been for a while now. We are still, however, at alert level advisory and aviation color code yellow here on the USGS update for the week. However, no active lava and no changes. No SO2, no tremor, no earthquake rates of concern there. So really nothing happening in Mauna Loa. We'll show you the plots here. Here's a tilt for the last week showing daily variations and an overall or slight increase. Here is a last month showing that we imagine a precipitation bump. Snow on Mauna Loa summit still covered in snow right now, and possibly more falling still. And otherwise, you see that long-term pattern of it's just rising here, rising. And you see that similar pattern on the GPS, north to south on Mauna Loa. You can see that after the eruption began there, had that jump, it essentially was contracting until at some point before the lava actually stopped coming out and it started building back up, and it's continued that trend. We're actually missing data here at this far right end of the plot. It seems likely that the weather has stopped the transmission of data to the website, right? But it's probably still being collected, and we'll see this filled in at some point in time. However, back to the USGS update, that's all there is on Mauna Loa. There's nothing else of concern to discuss here this week. So, quickly moving on to Kilauea then. Let's once again put on this live stream for you guys and just pan it back and forth. You see that this is that kind of northeast area of this western basin, and seems to be the zone of most gas effusion nowadays. And what we saw at the beginning of this most recent 2023 eruption was lava's coming into the pit from this side now, whereas in the past it was coming in from the other side over there, right? So that makes sense to see all this fume coming out from here near where the lava source is thought to be. The far right end of this lava lake over here, this little bay, has seemed to be completely inactive. We see the overturning event happening more in this inner basin here, where this little peninsula has built out into the basin here. So to give you an idea of what it's been like this last week, here's a KW camera showing day and night. You can see how sometimes you can see glow through the night, and sometimes it's just too cloudy to see anything. Right? Sometimes there's just no lava on the surface because it's in the middle of that overturning process, in between the processes, I mean. And then coming back on, you do see is lots of rainbows, right? Rainbow every day of the week. You can go on HawaiiTracker.com and see Dane's post of images of rainbows every day of this past week, which is fascinating. So if you're a rainbow viewer, viewing's been fantastic. If you're going for the lava, then not as much. It's not as glorious as it was a couple months ago here. So still some rain coming through. We can see visibility overall is better at the summit. Accumulation rates are not as high as they were back a couple of weeks ago, but it's been enough to mess with the cameras a little bit there. So that gives you an idea of what it's been like. You can see the wide angle view, all the fume. And that's why I like the thermal camera. And here's the F1 once again. I put it back 2 weeks so you can see that reduction in the eastern vent and central vents that continue to be completely inactive at this point in time, and only the western basin here is still active. So zooming into there so you can actually see that's the only place to look. You can see at this speed a little bit better the pulsing of the lake, how it seems to flash with the yellow or orange color, and then it goes back to the pink afterwards. And so that's kind of when the crust is forming in the surface there. So that's the F1, and I'll play it one more time, just so you can see the difference from 2 weeks ago when we still had this western embayment, this bay where the lava originally came out from the west vent in 2021 to 22. Was still active last week, and then here this most recent week, that seems to be cut off right around in there. So the area has contracted a little bit, and it's also going this overturning process and not undergoing the constant circulation that we saw coming in here. We did discuss last week how heavy rainfall was shown to actually induce spattering in the lava lake, right? So USGS didn't exactly propose a mechanism for that happening, but you imagine with all that extra water on there, you imagine it maybe can cool a little bit faster. And in that case, it could form the crust a little bit easier, and then it may actually trap the gas and force it to have these spattering or gas release in more episodic manner than continuously. But the caveat being the eruption has to be at just the right amount of sluggishness, right, for that to actually be visible. Clearly, if you have a big open lava lake and it's bubbling and really hot, then it can rain on it, and it won't make that much of a difference for very long. You can have an open channel from Ahu'aila'au and Leilani all the way down to the ocean, and it can be pouring rain, and it can have no effect at all on actual lava, right? So the lava's got to be at a certain, just slow enough rate for that to actually have an effect. But that may be what we're seeing at this point in time, where we do have a sluggish activity in that western basin, and we're having a lot of rain. Precipitation values aren't as high now, but the ground outside the volcano when it was saturated. Towards the volcano with all that heat, it's more debatable there. But if there is an effect of the rain at present, within this short, like 2-week time frame that we're talking about from 2 weeks ago to now, it's likely to be seen on the surface of this lake, and it's maybe slightly more sluggish than it could otherwise be from the rain. Might be how I would put it, and that's just based on what we know so far and my understanding of it here. So that is the F1. We'll show you a different view of the activity in the lava lake. Here's a V1 camera, and this is just all the way day and night, so I'm left in all the cloud obstructions so you can see how sometimes it's hard to see through there. And nighttime, daytime, similar activity as far as the pulsing. Sometimes it's black, sometimes it's glowing, sometimes it's hardened, sometimes it's open. And that's the last week here on the V1 camera. And so still a lot of activity to see in there. It's a lot smaller than the area we saw erupting two months ago. Still pretty interesting to see that overturning process. It is a little hard to see with the flashing in there, so what I did is take that and cleaned it, just the daytime images here. And let me put on a loop for this here so you guys can see. And what I'm hoping to show in this just daytime view is how you can see this movement of the actual crust there, right? So you can see the lava's coming in from this side. You can often see the stream coming in from there. But you see overturning events starting from the back end over here as well, somewhere in an area over here. And you also can see, if you look closely, maybe I can zoom it in more, as it's looping here, you can see how the crust is actually dropping occasionally when those overturning events happen. And it kind of swells back up and drops again, and swells back up and drops again, right? It's interesting to see that. And there's actually a little piece of rock here in the middle that's part of the crust that doesn't seem to be lifted as much. So when you see the crust lifting up, that area is staying still. The lava kind of rises up, floods onto it, rises again, that thing keeps sinking. So you kind of see a little bit of that pattern here in slow motion, and hopefully I've zoomed it in and cleaned it up enough for you guys to see that pattern. So even though on our live webcam it looks like it's just static, just sitting there not doing anything, when you speed it all up, here is a kind of activity that is actually happening in that lake. So lava could still be coming in enough to be inducing this activity. However, we also know that after an eruption actually stops being fed lava, it can go on doing this overturning process for potentially a couple of weeks before everything shuts all the way off. So the longer we go without actually anything else changing or signs of input of magma into the shallow area, it does seem like it could be more and more likely that we'll see another break in the action here. But only time will tell what Kilauea will do next here. We'll have to wait and see. And in the meantime, just look at these little clues and fascinating processes that are occurring before our eyes here. So that's the V1. I wanted to bring up the webcam view here. And this is from a little while ago, but there is a KW camera showing the summit view. And so right now I can hear it's pouring rain outside my window, but it looks like my house is off this way and all these clouds over there. But there's a gap right there. Clearly it's been raining. You see lots of steam and other gas coming up from the crater floor. I did want to point out one thing. I haven't showed you guys the B1 camera yet. But when you look at this view here, the B1 camera is now, so it's somewhere in here. Maybe it's somewhere in here. It's somewhere in the range of this side of the crater over here. And since the lava has filled the crater so high, we actually have this big wall of steam that's being emitted along that side there. So actually you can see right now, clear view on the KW camera. I'll scroll it down. There's our F1 camera showing a little overturning action happening. And so the one side is got fresh lava on that southeast side, and then this other side is more crusted over, starting to break through there. Coming to the V1, there is our clear view that we just saw streaming live. There is the S1 looking from the south. We're now looking at that eastern basin that's completely drained and inactive now. So lots of views up there. And then we come to the B1 camera, and it looks like this. And so you can see there is that wall of steam, and it seems like when we have this kind of event with this much water, the steam comes up just along that one crack in a wall, but it seems to be right in front of this camera. The camera is probably getting a nice steam bath every day. It's going to probably deteriorate a little faster now that that's happening there, but that's the story of the B1 camera, and I will show you the B1 camera now. There it is, but because of that wall of steam, you're not seeing a whole lot. We have used this view in the past for a proxy for viewing from the Kīlauea area, but the Kīlauea area is higher up and has a better angle in, so it's not exactly the same as this. You probably still see a lot more. You don't see this big wall blocking your view, like the camera does right at the edge of the crater here. Still, that's what's going on at B1. Interesting to note that change in visibility just because of the infilling of the crater over the last few years here. So, but that's the best we have for viewing. As Dane mentioned at the top, we don't really have many submissions. People are not going out in a volcano that much. When they are, they're enjoying the views that they can get and dodging rain, which sometimes is coming in sideways, according to some of the reports. I saw a report from one of our viewers, Solomon, came to visit and tried to go and look, but sometimes this doesn't work out. So, what can you do? Yeah, dealing with nature there. Still appreciate your comments. Let us know how your visit goes if you have come. As far as viewing, the last thing I'll say is just to make sure, if you are planning to come, to check the National Park website. They do have this notice, the activity is diminished since the 22nd. They do have all the orientation, live stream, all the links on there as well, maps of where to go and all of that. So at this point in time, you're probably better asking advice on an hour-to-hour basis from the rangers of what actually is visible and from where. So I won't spend any more time on that today here. In a national park, though, because of all the rain and because the eruption has wound down a bit, there's less fog coming out, and it's also not reaching anywhere where there are sensors very well. So everything's in the green. Winds or trade winds from the northeast today, and there's no need to go back and I can show you guys the charts here if you want. All green all the way down. Oh, actually here, and the China Craters Road showing some SO2, which is unusual. That's way down by the coast there. So not a whole lot happening on a volcano to be concerned about with the gas. More so, it's the weather that people are worried about now. The VOG forecast is this. So we actually have an SO2 emission rate down to 250 tons per day, which we'll talk about in a second. That's the most recent report from USGS from the 28th of February, which is way, way down. That's almost the background level there. That is not surprising given the sluggishness of the eruption here. But with that little gas coming out and the other weather, you can see that the VOG impact for the next week is pretty minimal. It does pop up here on a Mauna Loa flank, but not so much down to Ocean View and South Point even, which is interesting, right? Maybe a little spot uphill Pahala, but pretty good this week. So pretty minimal impact from the VOG, which is still the greatest threat to people from this eruption. Just to back it up, here is a capture from Purple Air showing mostly greens all around and a couple anomalies that are not volcanic to deal with. So that is the hazards for this eruption, or hazard summary there. Not a whole lot of hazard, seems the weather is helping and the emission rate is down. Okay, so moving on to earthquakes next. Also not a lot to talk about there. We've had a 3.3, 3.2, 3.0, 3.0 in the last week here. One of those is our typical Deep Pahala earthquake. Let's zoom this in a little more. It's right in there. One of these, 3.2 by Pu'uko, is offshore to the northwest. It's one of these settling events, so the island is adjusting to its changing forces as it's leaving the hotspot and cooling and contracting at the north end and being heated at the south end there. The 3.0 we have is actually down here on the south flank depths. And then the last one is a 3.0 here on Mauna Loa's southeast flank as well. Close to the surface, actually. And just little adjustments that are not too concerning as one-offs. If you were to see more earthquakes in these areas over time, then you might be more concerned, but on their own, it all seems to fit within a background pattern here. So that is it for the earthquakes, and with that, we'll turn to Kilauea monitoring. And I'll start once again with the USGS updates. I won't read all weeks. I'll just talk about the one that's issued today because it has summarized and is all the way caught up. However, it is stating much of what's been said the last week and over the whole week since. The summit eruption of Kilauea volcano within Hale Magma crater continues at greatly reduced activity levels compared to several weeks ago. While activity is confined to the crater, no significant changes along either of the volcano's rift zones. Right, so that's one thing that we're always emphasizing, is that people may get worried that the lava is not at the surface as much. It might be going to rift zones. There's still no sign of anything like that. It's all still in the summit. All the changes are restricted to the summit and underground at the summit. And we're not seeing any indication that anything elsewhere yet. Someday it'll happen, but we're not seeing that yet. So the lava lake observations. Eruption of lava on a crater floor continues to be greatly diminished. The central and eastern vents that were active earlier are not effusing any lava at this time. The western lake within a basin of the 2021-22 lava lake remains active but with weak circulation. It is mostly crusted over with intermittent crustal overturns. The reduction in activity is related to a large deflationary tilt signal that began on February 17th. Then a note, following that signal that lasted until the 19th, summit tilt meters have tracked several smaller DI events, deflation and inflation events. Over the course of these events, there's been a slight increase in net tilt, but the summit remains deflated compared to the period leading up to February 17th. More vigorous eruptive activity on the Hale Magma crater floor may resume when the summit reinflates to the prior level. So a little bit more diplomatic here. May or may not. We'll just wait and see. Tremor has dropped slightly in recent weeks, but it remains above background level. SO2 emission rate of approximately 250 tons per day was measured on the 28th. So that's key. 250 tons per day is a new measurement on the 28th here. Volcanic tremor has dropped slightly in recent weeks, but remains above background. That's the other important part here. And otherwise, nothing else in the rift zone. And so the hazards are all the same. So we'll move on to our graphs here and show you guys, starting with the last week. It's going to be hard to see much, but here's our last week lava depth. We see a bunch of noise in the data here, which once again throws off our scale. We can't really see any detail in here, so we have to move on from that. Not much to see. Here's our last week in summit tilt. This is all the small deflation and inflation events that the report refers to here. Small variations showing movement of magma within a system underground. But we have to zoom out to the last month to really make a little bit better sense of it. For the last month, the lava depth is also not as useful because we have now two different areas of noise, so still not much to see. Slight increase in level there. Can't really see the detail in here so much. And for the summit tilt, here is essentially our level before that rain and big tilt event. Here's a big tilt event that went from the 17th to the 19th. Right? We've speculated that could be some combination of rain influence and the actual real big drop of deflation. Even if it's just partially, you can see that the highest point we've reinflated to is somewhere in here, so we haven't seen enough, apparently, obviously, to actually see the lava return to the surface in any more active way than we've seen so far. Right? And you can see a little bit more drop in here too, and we just have to wait and see what happens, right? At Pu'o'o, on the East Rift Zone, where there is no magma influence there, we can see here is that rain signal from the 17th to the 19th. Those couple of peaks right in there. We might have another one coming in here at the end, and a little bit of a readjustment here, coming back down to level, right? So last week we talked a little bit about the maybe the length of effect of the rain signal on a tilt meter, and my memory at the time was a couple of days is when you would see that effect mostly, right? And I think on a tilt meter that is largely true, but it really depends on how much water and how long it's taking to drain out and all of that, right? So it seems like in this case at Pu'o'o, I would suggest you see the evidence that's lasting maybe a couple weeks in that case for it to actually affect that signal. The thing is, the tilt meters are on the surface of the ground there, and they're measuring the ground tilt, and obviously if the water is right next to it, it can have a stronger effect, and as it percolates down through the ground, it's getting more and more distance from that tilt meter, and you'd expect the signal to be dampened a little bit there. So some combination still of the rainfall, the rain rebound, if there is any yet, because it's kept raining and don't really know there. But clearly you can see that most of the signal on the summit plot is not showing this little noise, kind of fuzziness to the graph that you see here, right? On a Pu'o'o signal, that's what you see more and more in a weather-dominated signal here. So this one appears to still be the volcanic plumbing with magma moving up and down within the system and causing these transient pressure changes deep underground. So we're still waiting to see what happens when it comes back up. how far it comes back up, what happens at that point in time, and that's still the wait and see part of the story. Earthquakes are steady, not much to report. SO2, our most recent value, is down quite a bit. That was something that we saw during the events in early 2022 as well. We'd see big deflation events, stagnation of the lava lake, drop in SO2 emissions, and then it would actually come back at some points in time. Right at the very end, it obviously did not come back, but many times it did come back there. We'll just have to wait and see. SO2 at the summit, a little bit more detected here, but impacted by the weather as well. So for the last year, here's how it looks as far as earthquakes. We're kind of at the background level that we've seen for a long, long time. SO2, here is that most recent plot, almost back to zero, showing that full, so far, trend of the gas emissions for this 2023 eruption, which is now approaching its second month. A couple of days here, it'll be 2 months on. And most interesting, as I started off at the top of the broadcast, is this 1-year summit GPS here, right? So quickly, the Pu'o'o GPS here at the bottom, no real change, it's still going down. You really don't see any effect of recent activity. It's just still contracting. Rain is affecting the tilt signal, obviously, but not really changing much what's happening deeper underground. At the summit of Kilauea, here is that signal once again. So you actually see this was the eruption onset 2 months ago, and then a kind of deflationary phase here. It seemed like it had kind of stabilized. This little wiggle, I'm not quite sure there. It might relate to these big deflation-inflation pulses. But now, in the last couple of weeks, this is what really is interesting, is how it's coming up here. Maybe hooking back at the bottom again. Once again, maybe there is another deflation-inflation signal coming in here. This is something we saw in the past. Deflation-inflation signal is actually affecting the GPS when they last long enough. We've seen other adjustments earlier in the data as well that show a similar pattern. But the bottom line is that if we're seeing this signal, which is more sensitive to the deeper parts of the volcano, spreading still, and a tilt's not showing that same thing, right? We can then infer that magma's coming in still from below into the volcano, but it's not making it all the way to the surface of the lava lake. Some maybe still. There's still tremor above background, so some input into the lake perhaps could still be occurring, adding heat, adding gas, allowing that overturning to extend for a while, right? But more of it is building below ground and is actually getting out, and that's why you might see the signal in the GPS here. So it's not like the volcano is done. Like, if we saw this actually crashing or staying level, you might think, okay, well, maybe there is a gap or like a decrease in the supply. But this would suggest that the supply is still the same, and it's just a changes on a surface plumbing and dynamics of the conduit coming to the surface and all that mess that happens underground to lead it to be less active at the surface today. So that's the monitoring signals here. I'm going to pivot here, and I'm going to show you guys the last 5 years of GPS data here, right? So it turns out that USGS makes these nice 5-year plots automatically as well. At this point in time, we're 2 months ahead of the 2018 eruption 5-year anniversary. So a 5-year plot actually shows us a lot of what's happened since 2018. I thought it's a good time to look at this plot here. So at the summit, we had a little bit of inflation happening before that. This is all the summit collapse. It was massive over those 3 months at the summit here. And as soon as the collapse ended, we start to see re-extension of the summit caldera north to south. Magma was coming in, filling those void spaces underground, pushing its way to the surface, until eventually here, this little bump is the first eruption, December 2020. You can see a temporary relief in pressure there, but then it actually resumes very quickly, right? This eruption lasted from December 2020 up until May 2021. That whole time, that's the whole length of that first eruption there, and you can see that only in the very first part of it was a deflating. In most of the later months, it was actually continuing to extend, because once again, magma was coming into the volcano and it was not making it all the way out, but gathering underground, right, through some kind of, think of it as a clog or something towards the surface, right? So still building underground, but not as efficient getting to the surface. So the eruption actually ends here, but the signal does not appear changed. It keeps building up until you see in September 2021, the same thing happen again. Right, there is that little drop, very short lasting before, once again, after a little bit of slower rates pick back up again until that eruption actually ends in December 2022, right in here, right? So once again, most of the eruption was undergoing this inflationary character. And the last bump is what we just saw 2 months ago here, beginning 2023, and here we are at the right end of it right now. So that's the big picture. The big picture is that since that big collapse following 2018, magma has been coming in steady and pushing the volcano apart at a pretty steady rate. Underground, it's been filling pretty steadily, and occasionally it can actually make its way to the surface and pop out and be this spectacular activity we see at the surface. But underground, the story really hasn't changed a whole lot. It's pretty consistent there. So a lot more variation at the surface than you see underground. Now, since we're talking 2018, and we're curious about what might trigger that eruption, we're going to go through the possibilities here that have been published recently. And it all comes down to that break at Pu'o'o that allowed magma to move from where it had been for the previous 35 years down to the lower East Rift Zone towards Leilani, and we all know what happened from there. So more about what's happening beforehand will be the trigger, and then here we'll looking at what's happened since then. Right. So here's the actual inflation of Pu'o'o early on, this little bit right over here at the bottom. Then the whole thing gets wedged apart as magma shoves in there. And as it then erupts out of the lower East Rift Zone, the whole thing starts to sag back together, contract back together. And following the end of the eruption, it looks like it was about October, maybe a little before, but around in there where you start to really see the pickup in the extension rate, right? So magma was once again refilling that middle East Rift Zone. We do not see this same pattern lower on the lower East Rift Zone, so it seems like that lower part did kind of clog off. But Pu'o'o was a place that was developed a pathway from the summit for 35 years, and so we imagine that was a larger opening that you couldn't really clog, and so when the magma came back into the summit, it's able to reoccupy that area and push back through. And you can see it push back through from October 2018 all the way to October 2020 or so, right in there. That's when we started to see extra activity at the summit, suggesting the magma was intruding beneath the summit there. And once we see magma actually finding pathways towards the surface and new spaces at the summit, from that point on, October 2020 till now, this is a long decrease in a line like the Pu'o'o. So at the onset of that, we heard the USGS state that there was actually backflow. The magma was flowing from the East Rift Zone back towards the summit. And it appears that that pattern has largely been the same. At some point, you imagine that you probably run out of it, and it's basically just there's probably some disconnect as well. Maybe eventually you can clog it if you start doing this kind of funny business with the transport system underground. So in any case, there's been no change since 2020. The Rift Zone does not seem to be feeling or expressing any of the same patterns we see up here at the summit ever since this first eruption, right? The second eruption, third eruption, no signal at all in a Pu'o'o line here. So that's the monitoring, bringing us current since 2018. I thought what I would do is revisit Volcano Watch from last week as a stepping stone to our discussion here about the 2018 trigger. So let me pull that up on screen. Let me get it here. Last week's event was the missing slow slip events on Kilauea South Flank. Right, and the reason I bring this up is because we clearly saw a change in behavior of the South Flank since 2018. And even though the pattern is essentially the same, the fact that you were seeing enough sticking to actually induce these slow slip events, right? There was actually something catching to allow it to happen all at once in 24 hours. Even if it's not one earthquake over a few seconds, you actually see over 24 hours that whole slow slip event occurring. A quasi-earthquake, right? Showing that there actually was some stick to that south flank. It wasn't moving as much as it actually could, right? So it was going, but then occasionally it would not move as much, and then it would have to accelerate to catch up, and not move as much, and then accelerate to catch up. And recently, it's not been doing that, right? So the reason this is so important is because we've discussed before, there are two major factors here in a volcano, right? There's an actual magma pushing its way through the ground, but there's also gravity pulling a volcano apart through movement of the south flank, especially, right? The south flank can move. The south flank's upper portion is a rift zone, so when it moves, it actually can open the rift zone and allow more cracks to occur there, right? So that's how I wanted to start this off with just the emphasis of the south flank. And then I'm going to step back to the volcano watch from April 23rd, 2020, which was when the USGS first responded to this idea of the triggers of the 2018 eruption. So let's talk about 2018 eruption triggers now. So at the time, April 2023, there was a lot of coverage of the potential of rainfall actually having caused the 2018 eruption. Maybe not caused, triggered might be a better word. And to just lay that up top and distinguish it, right? The cause can be many different things coming together. The trigger would be the very last thing that actually caused it to go, right? So you could have, let's say, magma doing 99% of the work, and you can have the rain come in at the last minute or whatever it is, the last 1%, and that's the trigger that they're talking about as far as trigger, right? So sometimes people are using the word cause and trigger interchangeably, and it's easy, I just did it. But there are actually different things there, right? The trigger being that very, very last straw that breaks the back, and the cause being the whole buildup of everything that goes into it, I would suggest. So the USGS is focusing on magma pressure, and along those lines, they mentioned lots of overflows of the lava lake, April 2018 especially, but also this plot here that's showing GPS displacement in meters in the summit in red and Pu'o in blue, showing that you actually see a good amount, 20 centimeters of displacement in GPS over at Pu'o, and somewhere in the order of maybe 2 centimeters of displacement at the summit here, right? But clearly there's a lot going on. We actually saw the lava lakes at Pu'o overflowing and at summit overflowing at the same time. So it did seem like there was something going on there. The long and short of this volcano watch is that Hawaii residents need not be concerned heavy rain might cause an eruption, right? What their stance is that really, essentially, the trigger is less important than the whole cause of buildup, and the whole cause of buildup was mostly the magma pressure, right? And I think a lot of the data that they show does suggest that here. So, leaving it at that here and moving on, just show some of the coverage this got. This is a NASA blog, and actually NASA funded this research into the rainfall trigger of the eruption. And the reason being is that they have this program that is called, where is it here? The Global Precipitation Measurement, the NASA JAXA Tropical Rainfall Measurement Mission, right? Where they're trying to infer the rainfall in tropical areas from the satellite measurements without having to always have rain gauges on the ground. So that's why NASA is involved here. And that's why they're giving coverage to this here. And I'll just move on from that. I'm going to shift gears here, and I'm going to actually talk about, before talking about the rain, I'm going to talk about this paper, which was published 1 month after the original rain paper. This paper is by Ashton Flinders and others in Bulletin of Volcanology, open access here. It was published in May of 2020. So this, I think, is something that might inform both the other arguments that we see from the USGS and the University of Miami research group here. But let me highlight the important parts of this Flinders et al. Paper, which is noting seismic velocity variations actually change in association with that eruption here. So coming down here, while deformation data indicated the summit and the Middle East rift zone were inflating for previous several years, why Pu'o collapse and what initiated downrift deck propagation remains unclear. Using ambient noise seismic interferometry, we showed that a magnitude 5.3 decollement earthquake, that's a south flank earthquake, beneath the south flank in June 2017, induced a co-seismic decrease of up to 0.3% in seismic velocity throughout the volcano. Doesn't sound like a lot, but for seismic velocities, that's significant there. This decrease may have been caused by dynamic stress-induced shallow crustal fractures for example, weakening to dilatant crack growth, and was greatest near Pu'o'o. Additionally, they verify other increases in velocity right before the eruption as well. So, so let's see here. Consistent with increasing pressurization in a shallow segment reservoir. The increase occurred coincident with the first in a series of lower crustal earthquake swarms 6 days before a 2-month period of rapid summit and Middle East zone inflation. So these guys detect first a year ahead of time in June 2017 this 5.3 earthquake, which changes the properties of the whole volcano. We'll talk about that here a little bit more, right? But really, they say the whole Southwest Rift, Summit, and Southeast Rift all had this drop in velocity. All of them had the speed that earthquakes travel through the ground change, right? Why might that be? Well, if you move the ground out of the way, you might actually open little cracks. And if those little cracks, if you have more void space in there, then it's not as efficient to get the energy through across those little cracks. So you actually lose something along the way, right? So bottom line, what they're suggesting is there were a bunch of cracks opened up at the head of the south flank on the rift zone, greatest at Pu'o'o in June 2017, 1 year ahead of time, right? That was actually noted in the data, right? At the time, no one was saying, by the way, the velocities dropped today, let's all watch out. Like now, that's something we'd like to hear in the future if something like is happening again. But this is all in hindsight, of course, right? So looking back, they say back to June 2017, that was the actual, from the seismic point of view here, first domino that led to everything else occurring. So that's the bottom line there. Let me see what I had in this next tab here. So so this is the whole paper here, and let me see if I can find a figure. Summit, Southwest Rift, East Rift Zone. So okay, here we go. The green stripe here is like the error range of the analysis, right, of the signal. And you can see right here, this is the June 2017, where you actually see the signal drop, starts to recover. This right here is the eruption. It actually begins right there and going to here, but they have highlighted in gray earthquake influence, and in red eruption influence. There's actually 1 day of eruption that happens right here, but we actually also have this magnitude 6.9 earthquake which occurs right early eruption on the second day, and it has its own effects, drastic effects on the actual seismic energy there. The summit swarm that preceded the eruption is shown right here, and here you can see these signals, the summit, and not as clearly at the rift zone here, of changing properties 10 days or so, 2 weeks ahead of the eruption actually beginning. So in the future, this is something you can actually look at as, look, the rocks are so stressed that maybe at least in the summit area here, whatever cracks you did have now are all pinched closed because it's so pushed up against itself. That would suggest pressurization is responsible there as well, right? Not as clear to see that on a rift zone at that exact moment, but they're saying it goes back to 2017 actually there. Okay, so let's move on from this one. Just note that I don't want to dive too much into the weeds of all of these, but let's talk about the story of these papers, right? So the paper that we're referring to as a rainfall paper is actually titled "Extreme Rainfall Triggered a 2018 Rift Eruption at Kilauea Volcano." It was published in April 2020, and this is the preview on Nature here. Right, so we actually can see the abstract and a few of the figures. So they note, let me see here. They show infiltration of rainfall into Kilauea subsurface, increased pore pressure at depths of 1 to 3 kilometers by 0.1 is 1 kilopascals, its highest pressure in almost 50 years. We propose a weakening and mechanical failure of the edifice was driven by changes in pore pressure within the rift zone, prompting opportunistic dike intrusion and ultimately facilitating the eruption. So in this first version here, I'll say it. I'll see why I say this in a minute here. They say the precipitation-induced eruption trigger is consistent with a lack of substantial precursory summit inflation. Right, so they're saying there's not much summit inflation, And this intrusion, unlike others, was not caused by the forcible intrusion of magma into the rift zone. Right? I think that's a sentence that really got the USGS right there. It was not caused by the forcible intrusion of magma into the rift zone. Moreover, statistical analysis of circle eruption occurrence suggests that rainfall patterns contribute substantially to timing and frequency of Kilauea's eruptions and intrusions. Thus, activity can be modulated by extreme rainfall triggering edifice rock failure. And they note concern because of climate change here with more rainfall, right? So let me scroll down here. Actually, you can click on the side of these figures thing. I'm going to zoom this way in, and I'm just going to use these little previews they give us. Right, so here's an example. They're actually showing in these two plots over here on the left. This is the period 2014 to June 2017. Why? They note that June 2017 is when the behavior of the volcano actually changed. They actually say, look, before June 2017, when magma came into the volcano, you'd see inflation at the summit. Afterwards, here's June 2017 to May 2018, the period right before the 2018 eruption, and you don't see nearly the same per year vertical displacement, right? Talking about the verticals only here, as you did beforehand. And their dividing line was June 2017. It came out totally independently, right? It's published a month ahead of time. So they're saying, okay, well, something else is going on here. It's not the same as before. And I think that's hard to argue with, right? You look at these two plots and it's clearly not the same as before. So we just talked about the seismic velocity paper. They would suggest that was at 5.3 that actually moved the south flank is why you're actually not having as much vertical inflation. You might actually have a horizontal extension more so without needing to push it up. Why? Because you have made more space horizontally. So that's one possibility there. Or it could be a combination of that earthquake allowing cracks to open, allowing more rain to move through, right? Maybe the rain then can reach areas where it can contribute that last 1%, right? But we'll dig into that a little bit more. Here is rainfall in Kilauea, the plots they actually show. I'll move over that one. Diffusion, right? So here's their diffusion model. How is the water percolating through the ground? Which is very tricky, right? So we've discussed in the past how much uncertainty exists in Kilauea's groundwater, its host systems, like where everything is, which way exactly it flows, where it's building up, and all of that. We know that the summit has isolated aquifers that don't connect to the rift. We know that everything is kind of compartmentalized and bounded by these volcanic structures as well. So these guys aren't considering any of the lateral variation at all, looking at the vertical only, and it's a model, right? So Dane, I'll ask you for your line about models. What's the line about models? Say it so I can hear you.
Sorry, there it is. All models are wrong. Some are useful.
There
That's
you go.
a famous quote. I can't even remember who said it right now, but it was a famous statistician.
Yeah. So
repeated by a ton of people.
The model is useful to try to learn something from, right? In this case, we're focusing on vertical, but it's important to remember what we're not focusing on. We're not really incorporating any of that horizontal dispersion, which might be significant. We've just recently learned from other independent groundwater studies that there's freshwater springs like 1,000 feet below sea level offshore an island. So likely a big lava tube system is bringing water down to that elevation below sea level. So clearly horizontal transport is important. I'll just leave it at that, right? So we're not looking at that. However, here's where they actually see the change. This is depth beneath the surface. Here's 0, and here down is 6 kilometers down, 3 kilometers. This is maybe the range of the rift zone, like right through there. Right? So what they're showing is you actually can have pore pressure changes corresponding to, those 0.1 to 1 kilopascals or so, right? Which, by the way, is as we said last week, a fairly small absolute measure, right? Compared to the magma pressure itself, the magma pressure is in hundreds of kilopascals. So, like we said, we're talking about like maybe 1% or a fraction of 1%, and if so, is that the actual trigger that's setting things off, right? So, here's an example. I know it's kind of blurry, hard to read, but what they've actually done with this model is for 2018, which had rain January, February, March was all, even April was all pretty heavy, right? But they're actually looking at presumably some earlier, the earlier January, February rainfall here. And they're showing how there's actually a pressure wave that reaches 1 kilometer depth on the 26th of March. So, it's not exactly clear here, but you're looking at maybe weeks percolating down to that 1 kilometer depth. And this is different when I was talking about the tilt meter. I'm talking about the tilt meter at the surface. The further down it goes, the effect is decreasing. Now we're curious about at each depth, how far is it taking to reach that depth, right? As it goes all the way down through our very porous rock. So they're saying a few weeks, maybe a month to be generous, for the 1 kilometer down. It takes another month to reach down to 3 kilometers down, end of April. Another month to reach 4 kilometers down. Another month to reach 5 kilometers down. Another month to reach 6 kilometers down, right? So they're actually saying that this whole process overall to get down to these lower depths, even below where the magma is residing, it could be ongoing for months and months and months and months, right? So that makes it tricky, right? If the thing is going on for months and months and months, can you really say that it was the very last actual trigger? Or is it more of the background that's kind of just building up and growing on there? Or like, was that the 1%? Or was it the magma 1%? And that's where the terminology actually breaks down. And I think it's really pointless to really argue about it was one or the other. We can just say, okay, the magma could have this scale effect. And we also can see that rainfall can have a pore pressure effect. It is limited, of course, but if a volcano is primed and ready to go, then certainly it could induce an eruption. But so could the tides. So could any other little event that's not as big as a magma pressure, right? So it can happen, right? On this kind of timeline here. But that doesn't mean that it was like the last straw, right? I think that's where I wouldn't go quite that far personally, right? So then they actually, they note some other things, actually correlating their satellite data with the actual rain gauges. They do a lot of work to try to make that work, and I think there they go a little wrong as well. You'll see why I said that in a minute here. More model results here. But this one also important. They've gone back in time, and well, yeah, let's look at this one first. They've gone back in time and noted, based on their precipitation data, what are the wet times of Kilauea? And they come up with their own definition of actual window, which does not actually match our statewide definition, we'll say. And based on that, they say that it's more likely that eruptions occur during a wet season at Kilauea than in a dry season. A little bit more, right? Significant in their analysis, but not very many data points there. Still something to look at, and maybe there is something there, but it's going to take a little bit more digging to get to that. This plot, where did it go? Right here, that I didn't talk about on the left here. They've actually gone back to 1975 in this plot here, and try to model with what's shown here at the very top here is depth on the left, right? And so how far down you're having increase in pressure, and over what point in time. So you can see the pressure starts at the surface and kind of migrates over time. Time is going this way to depth, like we just saw there. And they try to correlate this with intrusions occurring in a volcano, intrusions and eruptions as well. And based on their analysis, the yellow bars on this plot below here are intrusions that did correlate with increased pore pressure at depth, and the gray ones do not. So they're saying you have intrusions that don't have any rain relation, you have rain events that don't have any intrusion relation, but you also have this subset of actually some events do seem like they're more likely to occur marginally with increased pore pressure. So once again, I'll state it, if the volcano is primed and ready to erupt, then that could be certainly something that triggers it, right? As could the tides, combination of rainfall and tides maybe, right? Double the effect. All those things are possible there. So really it came down to the pattern of intrusion historically, the pattern of these wet eruptions, seasonality here, the actual lack of inflation vertically at the summit. And one last thing they mentioned was they try to make a point with the 1924 eruption as well, but they actually missed the timing there a little bit. And I won't go into detail on that one, and I'll instead turn to what was published 1 month later, author correction by the Miami group, Mark Corson and Emelon here. And they note here, they're basically walking it back a little bit. They say, in the abstract of this article, it should have read consistent with the lack of substantial precursor deflation because a small amount, 2 to 3 centimeters of localized summit inflation was detected with GPS starting about 2 weeks before the eruption. And so this has implications for terminology. As such, it's not solely passive. Rather, it's a hybrid intrusion by both decrease in the stress owing to fluids and magma pressurization as well. So they walk it back saying, yes, there was magma pressurization as well. We agree, after all, on that. This suggests that infiltrating rainwater was not the only factor influencing the intrusion. Right, so there they go. They changed a lot of other terminology kind of likewise in there. They note a few other little maybe cosmetic changes here. One of the sentences says most rainfall occurs between 9th March and 25th August, and instead they should have said between 16 August and 5 March. A little cosmetic change there. The 24 activity was kind of a miss there. They note the eruption occurred in May, but lake subsidence occurred in February. So they tried to tie rainfall in April to the May event, ignoring the early February date there, right? So, however, they say that, well, if it actually was February, that makes it a wet eruption, so we're going to count it as one of our wet eruptions. And it just goes into the weeds a little bit there, because if you're going to start saying, okay, well, that earlier part of this eruption now is going to count, and we're going to count that, and then really every eruption has precursors and other things that can get really complicated and tangled in there, right? So there is that issue going on there with all of this, right? So we regret these errors and thank Michael Poland and his USGS colleagues for bringing them to our attention, right? So you can see that immediately what happened there was paper came out. Immediately, Mike Poland and USGS colleagues reach out. They say, wait a minute, like there's a lot of stuff wrong here. 1924 is wrong. The rainfall dates are wrong. There's somewhere else they note. Finally, owing to the production error, the y-axis units of figure 2C and E should be millimeters rather than meters. Left label should be D. Instead of D, should say E. So there's a lot of little cosmetic things, right? So they kind of really got off on a wrong foot, right? Where they had to correct those small kind of cosmetic changes. Then you hear the USGS reach out to them and say, well, 1924 is obviously wrong. They update their figure here, showing the inclusion of 24 as a wet data point there. And that was that stage of the process here, right? So what happens next is a Volcano Watch article. The USGS then prepares this publication. They issue this essentially response to that article that was published online February of last year, right? So it took a while. It was received back in June 2020. Went through a whole bunch of back and forth revisions. Finally got accepted for publication in October 2021. And finally published online February 2022. That's a pretty long process there because of this back and forth going on, right? And here we talked about, this is what we showed last week. They mentioned the magnitudes of the stress being insufficient, right? That really the magma is a lot more. And I won't go back into all of that here as well, right? They actually go through a lot of other stuff, right? Let me pull up this Nature preview once again. And we don't get any of the article or access there, but we do get, once again, we can zoom in on these figures a little bit. Right, so they're showing GPS data, showing really, look at how much the ground is moving from GPS. This is magmatic pressure causing this to occur. They show the increase in deformation rates at the various stations here. They show the rainfall distribution map, right? And note that the pixel that was selected by the Miami authors is this little square right in there. covers mostly this red zone with less rain, right? That's mostly on a dry side of Kilauea, on a Ka'u, the rain shadow side. Whereas the actual failure at Pu'o'o would be in this box over here, which as you can see is much more complicated with much larger gradients of rainfall, right? Also of issue is you can't really tell because it's very blurry, right? But the USGS is highlighting the stations used there, and there for correlation, right? Like you can see, like clearly there's not enough stations for rainfall given the gradient of rain here, right? Even the size of the box is a little problematic because you're getting multiple things going on in there. So that complicates things as well. So there was an objection to that. I think maybe if they had chosen a box over here and done the analysis there, it would have been initially more convincing. They do respond and actually analyze that grid and this grid and that one over here, and they actually do these two up here as well. And in the end, everything's about the same. So ultimately, the conclusions don't change. But I think for people who are familiar with the rainfall of the island, seeing the box in this area was kind of off-putting as well. Right there. They really are concerned with the area right in here, right? By Pu'o'o, where that failure actually occurred. Let's see what else we can. I think that's all we get here, right, from the figures. So that was the response there. And in the end, I think if we break it down, there were four things that were noted, right? One was the actual lack of deformation there. Two was this argument about the rainfall, right? So let's put this to rest about whether it was rain or not. This was issued March 15th, 2018. Was a discussion from the National Weather Service. And just in here, you can actually note this little paragraph. For January 2018 through the end of February 2018, rainfall total accumulations were Lihui, Honolulu, Kahului, Hilo. Hilo got 30 inches in 2 months, 260% of normal. So it does rain a lot here. These events are not unique to that year, but that was at what time? We can probably agree that it did rain a lot. I think we probably can agree that the summit did not inflate vertically as much as it did in the past. But in light of the earthquake that happened in June 2017, creating more horizontal space, maybe that's consistent. Maybe you don't have to push the volcano up if you can push it sideways more easily, right? Then the historical data, they argue about the timing of the window, whether when is the wet period, when's the dry period, how significant is it to have 60% as opposed to 55% of the eruptions falling in that wet period. So there it gets a little more muddly, right? But that data is more the historical analysis. It kind of doesn't have to do with 2018 as much, right? They're just going to show, like, look, it's possible that if it happened before, and intrusions maybe were existed before, then why not here, right? It really comes down to, for this particular 2018 trigger, the lack of deformation vertically at the summit, right? So that's the kind of the back and forth of it there. I thought I'd bring up another article which is unrelated, although one of the authors is in that on the USGS team here. This is a USGS article back from 2003. And this is totally unrelated, except it's just to show one of these complexities, right? This is groundwater level changes in a deep well in response to a magma intrusion event on Kilauea. On May 21st, 2001, an abrupt inflation of Kilauea volcano summit induced a rapid and large increase in the compressional strain. Water level simultaneously dropped by 6 centimeters. A water level drop is in contrast to what's expected for compressional strain from pore elastic theory. And therefore, it's proposed that the stress applied by intrusion has caused openings of fractures or interflows that drain water out of the well. Upon relaxation of the stress, water levels have recovered at a similar rate. Right, so what does it actually mean? Let me pull up the figure here. Here's an image of the well, Kilauea summit, groundwater table right there on top of it, and there is a slight drop in the lava level right there, right? So you'd think that if you squeeze all this water, it should come further up the pipe, right? That's what you typically would expect. But in this case, squeezing from the side actually might open up these gaps in between lava flows, and the gap doesn't have to open very much. They note that the 6 centimeter drop will be consistent with a 1 square meter area opening by where was it here? 15 millimeters or 1.5 millimeters, I think it was. I'll have to find that. Not very much. 1.5 millimeters for a 1 square meter area could have dropped down that thing, right? So I bring this up because if you are getting increased pressure and you are moving things around and the ground is all cracked from the earthquake as well, funny things can happen in there, right? The water can maybe get a little closer down to where it couldn't go, or maybe it's going somewhere where you don't expect, right? It's just, the bottom line is it's complicated there. So I'm not trying to draw any absolute conclusions here. I'm just trying to kind of lay it out, right? Clearly water can have an impact on pressure. Clearly magma has a stronger impact on pressure, and the fact that you have had many rain events without eruptions being triggered shows that the rainfall by itself is not enough. You've had plenty of eruptions without the rainfall from the magma, showing the magma by itself is enough. But you could have magma having a contribution from the rainfall both together, work together to actually drive that. There is one other thing that I wanted to mention that I don't have an image for here, but the reason this has even come into an area of research is because it's been shown that rainfall does increase earthquake rates in areas where faults are locked, right? Because the thing is, if you have a crack that's already there, right, and the crack is one side is pushing the other and it can't move back and forth. Now, if you can actually wedge a little bit of water right in between there, suddenly those things can move a lot easier. So you actually can push water into those cracks deep down. You can actually, in some ways, not exactly lubricate the fault, right? But actually, the pore pressure allows it to reduce the friction on it so it actually can move. And that may be one of the ways the rain is also affecting this whole system, right? I mentioned the 6.9 earthquake. It happened on May 4th of 2018. That fault plane is down at 6 to 8 kilometers down, right? And we're seeing that water is reaching that level, perhaps. It's modeled to reach that level, so it maybe could get down there, and maybe the rain had an effect on the earthquakes. The earthquakes had an effect on the eruption. Maybe it's all tied together in some funny way like that as well, right? So that's kind of just throwing it all out there. You need to have the magma pressure. Volcanoes got to be doing something, but if that's the case, and an earthquake changes the whole conditions of the volcano, the properties substantially, and you have a whole bunch of rain happening all together, that seems to be what people are finding about 2018 Kilauea, right? So I don't have an answer for what the actual trigger was. Something caused that earthquake that happened on April 30th at Pu'u'o, right? That happened after magma intruded. There actually was a short rift eruption on a west flank of Pu'u'o before that thing broke open, and we saw signs of magma going down towards the lower east rift. So it was all about that one moment in time, April 30th at Pu'u'o. What led to that April 30th break? Everything else is kind of a consequence of that, right? Maybe if you just had that break and not the 6.9 earthquake, you wouldn't have had a whole summit collapse. You wouldn't have had such a long eruption with so much lava coming out. Maybe the rain had an effect on causing the earthquake, and in that case, really led the eruption to be as bad as it was. It's hard to tell that, right? But the stage had already been set, and that's evidenced really if you go back to the 2008-18 lava lake, its emergence showing increased activity on Kilauea for the previous 10 years ahead of that, right? So I think maybe we can agree the magma did most of the work, but what actually triggered it, who knows? It'll be a lot easier. I'll pull up one last volcano watch here. A lot easier once we have the results of this AEM study, this airborne electromagnetic and magnetic survey, right, where they actually fly the big loop under the helicopter over the volcano. One of the things they're trying to do is actually map out the groundwater, right? And so if we actually have an idea of what's happening there, we can perhaps revisit this whole discussion of how important was each of those factors, accepting that all those factors contributed to some degree to the eruption down there. Since we were talking about Volcano Watch, I thought I should just load here and see if the USGS has released this week's volcano watch. It looks like they have.
Yeah, it came out. It's on Mauna Loa and the some of the chemical signatures that we're detecting in there.
Seeing inside Mauna Loa for the first time in almost 40 years. First lava sample in 40 years. And since I haven't had a chance to read this, we'll just let you guys know this is posted on hawaiitracker.com, or will be shortly.
No, it's up. I can check it out there.
Awesome.
Yep.
And yeah, we'll maybe discuss this in more detail next week here. And talking about the actual chemistry changes on Mauna Loa. The lavas were of similar compositions to other eruptions since 1843, with slightly lower magnesium oxide, 6.28%, and temperature thus a little lower to 1155 degrees Celsius. All right, we won't try to pull any more out of that here at this point in time. We'll just wrap it up here by talking about community, and there are events happening in National Park this month, but there are none within this next week, so I'm going to skip that here this week, and instead just turn to actually a USGS public meeting coming up on March 15th, seeking public input on an environmental assessment for the USGS facility in Hilo. So this is to be on state land in Hilo, associated with the University of Hawaii in Hilo there. And it's also going to be, besides the geologists, also the Pacific Island Ecosystems Research Center, Pierce, right, which is a biology division there as well. So jointly occupying this new building.
Yeah. It's a great spot for it. I mean, it really is up there. It's above the campus of UH Hilo. It's an unused spot. I think there's only really one build. At least when I was there was only one building up there, and that was the EPSCoR building. And it up at that spot would be great for them, right? And the thing I like about it is it's not in a super high risk area like, say, the site of the caldera on the world's most active volcano, or in one of the most dangerous tsunami inundation zones in Hilo, right? I like it that they're kind of in an area that's not super high risk for anything in particular.
Yeah, there have been Mauna Loa eruptions that got in there in the past, but as we know in that area, there's time to deal with that if that were to be the case. It's not like a sudden, here comes a tsunami.
Yeah.
And all your servers are compromised.
Yeah. It's not ideal.
Yeah. So you can review online through March 28th, right? There's links there. You can find this. This is also on hawaiitracker.com, how you can get to these links. Or there's also going to be an open house on March 15th, 5 to 7 p.m. at the USGS Hilo Ironworks building in Hilo there. So that's where they will present and share more about the project and answer questions. Offer copies and all that. So that is just the heads up for March 15th. If we have any more to discuss, and we'll bring it up next week here as well, but that is the community message we have for you guys this week. And that is it, Dane, after more than an hour, once again.
Yeah, we didn't do well in that short thing, but that's normal for us. All right, we do have a bunch of people we want to thank. We had some donations come through. Want to thank them. I want to thank everybody that turned out first and foremost. We rely on viewers like you to get the message out there, and all that to help with the algorithm and all that stuff with Facebook and YouTube and everything. So appreciate everybody that tuned in today. Do want to recognize everybody that did the super chats. We had Chris Kiki, who came through with a $50 super chat and said, "I can't stay tonight. We'll watch on replay. You're both spectacular and appreciate it with all you do to keep us updated." Thank you. Appreciate the support there, Chris, the returning supporter. We have Josh WA with a $99.99 super chat. Says, "This is always great and informative. Really appreciate that big, $100 donation there, Josh." And then our longtime supporter, Gary Bryan, came through with $35. Says, "Thanks to Phil and Dane for these updates. Piggybacking on two pineapples, what is the relative scale of the edges, i.e. height, of the foundering pond?"
The edges of the it's hard to say. It's always been more or less 10 meters, 30 feet or so, I want to say. That's the ballpark that we've seen in the past. It's changing all the time, so I don't have an actual USGS laser rangefinder based answer. I can just say that in the past when we've asked that, it's always come back about the same, about 10 meters, about 30 feet. That's my best guess. It is a guess.
All right. So yeah, appreciate everybody that tuned in, super chats, and all that. We also want to thank County of Hawaii. They have helped make this content possible with the 5x grant to fund this live stream, as well as our short videos and the content that we write up and put on Hawaii Tracker. We really appreciate them, sticking their necks out on a program that's not exactly fit into the box, right? And I think it's proven itself worthwhile, and we appreciate them taking the chance. So yeah, I think that gets us through the all the donations and everything, and there weren't really any that many questions that were pressing for what we were doing. I was able to answer most of them in chat.
Good job.
So yeah, I think we can try and end there. And we will be back next week at 5 p.m. Hawaii Standard Time on Thursday. That's our normal time, unless something happens, and we'll go live. Big earthquake, anything along those lines, surprise eruption, we'll go live. But if barring that, we'll be back next week.
Yeah, sounds good, Dane. Yeah, and yeah, unless there's any last minute kind of scheduling issues as well, there's besides volcano stuff, other things happening as well. So occasionally we do have to bump things, and not expecting it yet, but sometimes it happens as well. And got some things I'm trying to juggle here. So until next week, from HawaiiTracker.com, mahalo you guys for all your support. Thanks for tuning in. From HawaiiTracker.com, he's Dane DuPont. I'm Philip Ong.